right, we're going to solve this problem right here to figure out what the voltage response is. This is going to be a natural response. And we've got these components set up. R, L, and C, they're all in parallel. The capacitor is 10 nanofarad. The L is 250 millihenry. But we're going to solve this problem 3 different times for 3 different R values to represent the 3 different cases that we've talked about. I'm not going to tell you which is which. We'll just figure it out as we go along. And here's some additional information that we're told, and this applies to all the problems we're going to solve. I sub L at 0 is negative 30 milliamps, and V sub C at 0 is 90 volts. Okay, so given that right there, we should be able to figure out a few things. One of the first things that you have to do is you have to compute alpha. And alpha is going to be 1 over 2RC. Now that depends upon R, so that depends upon which case we're going to work. However, omega naught is going to be 1 over LC. I should say omega naught squared is just going to be 1 over LC. And that depends upon the L and the C, which are not going to change for the 3 problems that we solve. So if you do this computation, this turns out to be 4 times 10 to the 8th. For omega naught squared, all right? So we'll need to compute alpha for each of our 3 cases, and then we'll need to do the comparison to tell whether or not we're going to be overdamped, underdamped, or critically damped. Okay, so I'm going to leave this sheet the way it is. Let's see, we know that I sub L is going to be negative 30 milliamps here. So I should be able to figure out what all of the other things are as well. For example, I sub R at 0, well, that's just going to be the voltage at 0 divided by R. And the voltage at 0, we are told, is 90 volts. So that's going to be 90 volts divided by our 2K, so 2,000 ohms. And that turns out to be 45 milliamps. Okay, now based upon that information, plus the fact that I am told that I sub L at 0, I'm given that value as minus 30 milliamps here. And oh, by the way, I should have drawn these. That's I sub C, that's I sub L, that's I sub R. And you know that as part of the problem. All 3 of those currents are coming down from that top essential node up here. So given that, then, you should be able to compute I sub C, because all 3 of those currents, I sub C plus I sub L plus I sub R, add up to be 0. And that should be true for all time. So at 0, I sub C is just going to be minus I sub L at 0 minus I sub R at 0. And this is going to be minus, and I sub L is minus 30 milliamps, minus I sub R, and I sub R is 45 milliamps. So this is going to turn out to be, that's going to be positive 30 minus 45. It's going to be negative 15 milliamps here. All right, so I'm just spending a little time before I really dive into the problem, sort of figuring out some initial conditions here. And all 3 of these are going to change depending upon what kind of problem, which of the 3 cases we have, because I sub R depends upon R there. All of these depend upon that. The only one that's fixed for all 3 cases is going to be that one right there. All right, so alpha. Alpha is going to be 1 over 2RC. That's going to be 1 over 2 times R, 2,000, times C, and that's going to be 10 times 10, and that's nano. Do you remember what nano is? That's 10 to the minus 9. This is going to end up being, according to my calculations, 25,000. Okay, that makes alpha squared equal to 6.2 times 10 to the 8th. Now, omega naught squared, we computed that, is 4 times 10 to the 8th. So omega naught squared is 4 times 10 to the 8th. So we can see here that alpha squared is greater than omega naught squared. All right, which of the three cases is that? This is something you need to know off the top of your head. You need to be able to recognize after you do the comparison here which of the three cases it is. And it turns out to be the overdamped case. Okay, if it's the overdamped case, then we know the general form of the solution is going to look like V of t equals A1 e to the minus S1t plus A2 e to the minus, I'm sorry, I put the minus signs there. They don't belong if I'm just putting the s's there. S2t, there. It should just be S1 and S2. The values computed for S1 and S2 will turn out to be negative. So the sign's included in the variable there. Okay, in fact, when we do that, S1 is going to be negative alpha plus the square root of alpha squared minus omega naught squared. And plug in for this alpha, plug in for this omega naught, and you get a value out of that that is negative 10,000, and that's going to be radians per second. S2 then is minus alpha minus the square root alpha squared minus omega naught squared. I'm not doing these computations right now, I'm just writing them down. You should do the computation yourself to confirm that that is the case. The units here are going to be radians per second. This one turns out to be minus 40,000 radians per second. Okay, so we've got our S1 and our S2 now. We could plug those in there. We still need our A1 and our A2. All right, well, how do you get that? Well, V at 0 is going to be equal to, well, just evaluate this at t equals 0. It's going to be A1 plus A2. And we know that V is 0 based upon our voltage across the capacitor at 0 is 90 volts, but that's where the energy is stored when the switch is closed, when this circuit starts doing its thing. So what does that mean? That means right at t equals 0, the voltage across everything has to be 90 volts, all right? So because everything's in parallel. So A1 plus A2 equals 90. There's one equation that we're going to use to figure out what our coefficients are. The other equation involves the derivative, dv dt, evaluated at 0. Now when you do dv dt, you're going to end up with S1A1 plus S2A2, and that's going to be equal to I sub c at 0 divided by c. So this is going to be the minus, I sub c at 0 was minus 15 milliamps divided by c, and c was 10 nanos, so it's 10 times 10 to the negative 9 farads. Do that calculation there, and here you've got two equations, two unknowns. You know what S1 and S2 are, so you can plug in for those. Okay, now when you do that, let's see, you end up with values for A1 and A2. I expect you to be solved for these, but I'm just going to jump to the solution. A1 is 70, and A2 is 20. So given that, we can write voltage as a function of time in this problem is going to be 70 e to the minus 10,000 t plus 20 e to the minus 40,000 t volts. There's the voltage response for our problem here. Okay, let's say you need something else. You need more information. Let's just do one more thing. Let's say I sub L as a function of time. What is that? Well, you could solve for that. I sub L, which is going to be the 1 over L integral V dt plus I sub L at 0. You could do that. What is I sub L at 0? That's the negative 30 milliamps. So you've got this term. Plug in the voltage here, do the integration, and that's, you got it. Okay. You could also realize that I sub L at t of t is going to be minus IR of t minus IC of t. Now, if you knew what IR of t was and you knew what IC of t was, you could just subtract the two and you could get it that way. Let's do that. And that'll force us to figure out what all these currents are as a function of time. So let's come over here. I sub R of t is just going to be V of t divided by R. So you just take this function here, divide it by R, and remember what R was. R was 2k. So this is going to be 70 e to the minus 10,000 t plus 20 e to the minus 40,000 t divided by 2,000. And that'll give you, you can do this computation and that'll give you some values. Okay. I believe that that turns out to be 35 e to the minus 10,000 t plus 10 e to the minus 40,000 t, but that's milliamps. Okay. So I sub R of t is given by that. Okay, what about I sub c? I sub c of t, we know that that's going to be c dv dt. So that's going to be c. C is 10 times 10 to the 9th multiplied by 70 e to the minus 10,000 t plus 20 e to the minus 40,000 t. You can do that multiplication too, and you'll end up with, oh wait a minute, that's the voltage function in the first place. You have to take the derivative of this, so I don't really have room here. You need to take derivative with respect to time of this, then multiply it by c. All right, I'm going to let you do that. Okay, but that is going to end up being negative 7 e to the minus 10,000 t minus 8 e to the minus 40,000 t milliamps. There. So what does that mean? That means that we can take I sub L of t, and that's going to be minus 35 minus negative 7 e to the minus 10,000 t. I'm doing this. Now, remember, it's negative r, so it's minus 35, and then this is already negative, so that's why it's minus a negative, e to the negative 10,000 t, plus, let's see, it's going to be negative 10 minus negative 8 e to the negative 40,000 t. Okay, and units are going to be milliamps, so do that. 35 plus 7 is still going to be negative 28 e to the minus 10,000 t. That's going to be negative 2 e to the minus 40,000 t milliamps. So here is what I sub L of t is. Okay, but along the way we figured out what I sub c of t also is, and we figure out what I sub r of t is as well. So we've got all of our currents and we've got our voltage. So we're pretty much done with this first one right here. Okay, let's do another one. Maybe we won't go into so much detail on the others because a significant portion of the work has already been done. All right, alpha is going to be 1 over 2RC, and if you plug in for 2.5K, then that's going to be 1 over 2 times 2.5, 2500. times c, which is 10 times 10 to the negative ninth. Do that calculation. Alpha comes out to be 2 times 10 to the fourth, which makes alpha squared 4 times 10 to the eighth. Okay, remember what omega naught squared was. Omega naught squared is 4 times 10 to the eighth. So what does that mean? That means these two are equal to each other, and that means that alpha squared equals omega naught squared. Which case is this? Critically damped. So this is the critically damped case. Since it's critically damped case, we know the general form of the solution. You immediately jump to the solution. d1t e to the negative alpha t plus d2 e to the negative alpha t, like that. So you know that that's the general form of the solution. You know what alpha is. You just computed it up here. So you're left with figuring out what d1 and d2 are. All right, based upon initial conditions, V at 0, we said that that is 90 volts across everything. Okay, that needs to be used whenever we're figuring out what this voltage is. So let's figure out what the voltage is at t equals 0. So take this, evaluate it at t equals 0. The exponentials go to 1. This t here goes to 0 as well. So what are we left with? d2. So we got d2. d2 is 90. All right, that leaves d1. And in order to figure out, it's going to involve the derivative. So we need dv dt. We're going to have to evaluate that at 0. That is equal to I sub c at 0 divided by c. And that turns out to be, when you do this derivative here, d1 minus alpha d2. Okay, so this right here, that is going to be how we get to d2. I'm sorry, d1. We've already got d2 up here. Now we need I sub c at 0 in order to do this. So we've got to rely upon our circuits knowledge. I sub c at 0 is going to be negative I sub L at 0 minus I sub R at 0. So we know what I sub L at 0 is. It's negative 30 milliamps. So we're going to have negative 30 milliamps minus the I is always going to be V over R for a resistor. So that's going to be V at 0 over R. So that means this is going to be that's going to be positive 30 milliamps. The negatives cause that to happen. And this is going to be 90 over 2500 because our R in this case is 2.5K. Do that evaluation. This is going to be 30 milliamps minus, that turns out to be 36 milli. So this is negative 6 milliamps for I sub c. Then we can go back up here and we have negative 6 milliamps divided by c, which is 10 times 10 to the negative ninth farads, is equal to d1 minus alpha. Now we know what alpha is as well. That's 2 times 10 to the fourth times d2, and d2 is 90. Out of this, that's d1. Out of this, you can solve for d1, and you end up with d1 equals 120 times 10 to the fourth for d1. All right, now let's figure out what the voltage is going to look like. It's going to be V of t is going to be d1. We could write that any number of ways. 120 times 10 to the fourth is one of those ways. T. Now we've got plus d2. Plus d2, that's 90. And let's multiply all that times e to the negative 2 times 10 to the fourth, 2, 1, 2, 3, 4 T volts. There. So there's our answer for the critically damped case. Okay, so we're done with that one. And we could go through the same process that we did in our previous problem, figuring out what I sub R, I sub C, I sub L are. You could go through that process if you wanted to, and these will be slightly different because we have a different R value. All right. Then that leaves us with the next case, where we've got R equals 4.2K, 4.16K. So let's go ahead and do that one now. Alpha is 1 over 2 RC, and that turns out to be 12,000. So alpha squared is 1.44 times 10 to the 8th. I'm going through this pretty quickly because it's the same general process. Omega naught squared, if you recall, is 4 times 10 to the 8th. Okay, from right here. All right, then what do we have? Alpha squared is less than omega naught squared. Okay, which case is this? This is underdamped. So this is the underdamped case. All right, since we know it's the underdamped case, we jump immediately to the solution. The general form is B1 e to the minus alpha t cosine omega sub d t plus B2, that's a 2. I know it's messy, but that's a 2. E to the minus alpha t times the sine of omega sub d t. Remember what omega sub d is? That's the square root of alpha squared minus omega naught squared, but you take the absolute value of it. If you plug that in, that turns out to be 16,000. Okay. Then, what's V of t look like? V of t is going to look like that with omega sub d plugged in. I just write it out. E to the negative alpha, 100, no, it's 12,000. 12,000 t times the cosine of 16,000 t plus B2 e to the minus 12,000 t sine 16,000 t volts. Okay, we're not finished yet. We still need to get B1 and B2, and we get that from the initial conditions. First of all, what is that voltage at t equals 0? We know that that's 90 volts. We were given that right here. It's voltage across everything. And if you evaluate this at t equals 0, the exponentials go to 1, the sine goes away, the cosine goes to 1, we're left with B1. So we know what B1 is. B1 is 90. The second one involves the derivative of the function evaluated at 0. And we know that that's I sub c at 0 divided by c. Okay, we need to figure out what I sub c at 0 is. And hey, that's going to be minus I sub L at 0 minus I sub R at 0 divided by C. And that's going to be minus negative 30 milliamps. Where did that come from? Right here. What was part of our initial conditions given to us? Minus, okay, now we need to figure this out. This is just V over R, and V is 90, and R was 4.16. 4160. Okay, so there. Do that calculation right there. Oh, we need to divide that by C, which is 10 times 10 to the negative 9th farads. And when you do this computation, you end up with 840,000. The units are going to be volts per second. And that's what I sub c evaluated at 0 divided by c is. Now, you set that equal to the derivative. So you have to take the derivative of this up here, and you have to realize that this is a product, so you're going to have to use product rule up there. And you should be able to compute what B2 is, because you already have B1, you plug that in as well. And when you do that, I'm leaving it up to you to practice this. By the way, you should practice this. Turns out to be 120. So what does that mean? That means that our voltage as a function of time is going to be, well, let's see, 90 times e to the minus 12,000 t cosine 16,000 t plus 120 e to the minus 12,000 t sine 16,000 t volts. There's our solution. So what's that going to look like? Well, we've talked about this before. The sine and the cosine are going to contribute to the oscillation. The decaying exponential is going to cause it to decay over time. So let's graph it right here. That's going to start at t equals 0. That goes to 1. This goes to 0. At t equals 0, this is 1. The exponential is 1. So we're starting at a positive 90 volts. And then it goes through its cycle. I'm not going to be any more careful than that. And it ultimately reaches 0 in the limit because we're multiplying by these exponentials in both cases. So as t gets larger and larger, the sine and cosine just continue to go through their regular cycles, but these decaying exponentials will win. Exponentials always win, and it's going to drive it to 0 in the limit. Okay, so we've worked our 3 problems now. That's probably sufficient for us. From this, we could go and we could calculate the currents for everything as a function of time to see what those are. But we've already done that for our first case, so it's the same general procedure to keep doing that. Okay, so we worked our 3 problems for our 3 cases, and all of these so far have been natural responses. Next time, we're going to turn our attention to the step response, but we're going to rely upon the information that you've already learned here. So if you don't understand this, I recommend that you go back and try your best to absorb all of these 3 cases, because when we get to the step response, we're going to rely upon this. All right, so hang in there. We're almost through the semester. We're certainly on the downside, and see you next video.